are talking about 3.2 permutations today. So what is a permutation? A permutation of n different elements is an ordering of elements such that one element is first, another is second, and third, and so on. When we are doing this, we also want to think about factorial. So that is maybe a brand new word to you, maybe not. Anything with an exclamation mark is factorial. And you take itself and all the integers smaller than it down to 1 and multiply them. So in this example, 5 factorial is 5 times 4 times 3 times 2 times 1. And then that is 120 if I multiply that. Okay, so let's look at this first example. Here there are 4 candidates for a job. The members of the search committee will rank the 4 candidates from strongest to weakest. So how many different outcomes are possible? So we want to think about how many options are there for the first position. Well, there's 4 different candidates, so 4. Then we pick somebody for that position. So now you have how many to choose from? Well, you have 3 to choose from because you picked someone for that first position. Okay. Now you have chosen someone for that position. So you are ready for the next position, which means you only have 2 to choose from. And then lastly, you choose someone to sit there. So now you only have 1 to choose from. And so then we multiply those together, kind of like we did with the counting principle, to get 24 outcomes. So this is also known as a factorial. So 4 factorial is 4 times 3 times 2 times 1, which is 24. Make sure to practice in Desmos that you can do 4 factorial in Desmos. So make sure that you can do that. Okay, next up we want to talk about telephone numbers that have 10 digits. So you have your area code. Around here it's 859, and then you have the next 3 numbers for the local telephone number, and then the last 4 can be anything, right? So it says how many different telephone numbers are possible within each area code. So let's take 859 for example. And so we're going to talk about how many different phone numbers can be created from that. So first, make sure that you know that there are 10 digits. Think about your keyboard. That's why I have that little picture there. There are 10 different digits that each spot of your phone number, so each 10 space of your phone number could be. However, we're within one area code, so we're within 859. So we're not really going to count those first 3. We're only going to look at those last 7. Okay, so how many options for the first position? It can't be 0 or 1, so I'll cross those out. I count that up, and I get 8. Okay, think about the next position. I can choose any of the numbers because my only stipulation was that the very first number cannot begin with a 0 or a 1. So I have all 10 numbers. I get to use those numbers over and over again, so each one is 10. Keep on going, because again, I can repeat numbers. Like if my number is 111, 1111, according to the stipulations in this example, that is an okay phone number to have. We of course multiply all that together to get 8 million different phone numbers. Okay, what about racing horses? So we have 8 horses here. How many different ways can they come in first, second, and third place? And we're assuming there's no ties. We're also not necessarily finding probability, because probability that a horse wins, some horses are more likely to win than other horses. So that changes things a bit. But right now we're just talking about what are all the possible orders that it could come, who got first, who got second, who got third. So first place, I could choose from 8 different horses. Okay. That horse gets first place. Now how many horses can I choose from? 7. I choose that horse. Now how many horses can I choose from? 6. And now I stop because I only want to know come in first, second, and third. I'm not saying all the way down to first place, just in first, second, and third. Multiply those together and I get 336 ways. Okay. Those red X's, I know they're in a very random spot. It was just a random horse gets chosen. Okay. Now, we have a formula here that says permutations, and here's what it looks like. So permutation is NPK, sometimes that's with parentheses. You have this on your notes sheet. So let's look at it in action. Let's go back to the horse example. Okay, so if we revisit the 8 horses, and we use the 8 horses as the N and 3 as K, some of our work looks like this. 8 factorial over 8 minus 3 factorial. That's the same thing as 8 factorial over 5 factorial. And so working that out looks like this. Notice there are things canceling. My PowerPoint's working ahead of me. Went ahead and canceled the 5s, the 4s, the 3s, the 2s, and the 1s. So I'm left with 8 times 7 times 6. Notice that's the same thing that I got on the page before it. So, ta-da, 336 ways. But wait, that was a lot of algebra, and we have not done that much algebra, actually arithmetic, since we've been in this class. We have relied on Desmos. Can we still rely on Desmos? The answer is yes. Here's what it looks like. So on Desmos, you will have to bring up your little keyboard here. You will go over to functions, go over to stats, and you will see the NPR. When you type it in, it kind of looks like this, and it opens the parenthesis, and you will put your 2 numbers in. Make sure always put your bigger number first, or else you won't get an answer. So in this case, 8, 3, and notice, hey, I did get 336 ways. Okay, so pause the video, try it. Just because you watched me do it does not mean that you're a master at it, so go ahead and try it and become a master. Okay, next we're going to talk about distinguishable permutations. So that's when, elementary school, I felt like I did this a lot. Maybe you did, maybe you didn't. How many words can you make out of the word morning? I don't know, whatever. And so distinguishable permutations is finding how many permutations can be made, but it takes out the repetition. So like if I have the same letter repeated, we have to account for that and divide that back out. So here's what it looks like. So if I have banana, I have the number of letters in the factorial, the frequency of each factorial, it's divided by that. So thinking about banana has 6 letters. The letter A repeats for a total of 3 times. The letter N repeats twice. And so here's what my formula looks like. 6 factorial, because that's the number of letters total, divided by all of my repeats multiplied together. So 3 factorial times 2 factorial. I could also even get technical and like not, I could even count the ones that appear once. So like B occurs once. So I could also multiply that by 1 factorial. Not necessary though, because 1 factorial is just 1, and I multiply by 1 and it's the same thing, right? So here's what that looks like if I'm doing it by hand. I get some things that cancel out. 6 times 5 times 4 is 120, divided by 2, 60 ways. Okay, and again, can you use Desmos? Yes, this is what it looks like when you type it in Desmos. Exclamation mark is shift 1, nothing fancy, but make sure to try it. And then this will wrap up the 3.2 notes, so you are ready to move on.